Okay, I think we've got everybody here. So this afternoon, I'm going to talk about some very important, a very important topic. If we want to get good performance using these multi-core architectures, like the Interlagos and Sandy Bridge that we've been looking at during this workshop, and you will have already seen, particularly during the exercises and during the talks, you'll have seen some strange behavior, particularly when you try to use, say, 16 threads on Sandy Bridge and you don't see the sort of speed up you might expect to see. So, and you've seen people talk about affinity and whatnot. So now I'm going to go into some more detail on these topics. Oh. And I'm going to turn that on. So I'm going to start the talk today with just an overview of the Interlagos and Sandy Bridge topology and point out some key similarities and differences between the two architectures, and we'll start to get an idea about how some of these features might affect performance when we try to scale to using multiple sockets. We'll have a look at what we call our NUMA effects, and then we'll look at something called our CPU affinity and memory affinity, where we can get more fine-grained control of exactly where our threads, like which cores our threads are running on, and finer-grained control over where exactly in memory we store the data that we want to operate on. And then we'll look at we'll do some methods and exercises to illustrate this point. And then at the end, we're going to do some extended examples where we're going to revisit the Laplace and dispersion examples from yesterday and see if we can make some changes to the code to get some good performance increase when we go from 8 threads running on one socket to 16 threads running on 2 sockets. So far, I'm pretty sure you've got the impression from the work we've done so far that these multi-core and many-core processors have really quite complicated architectures. You've got these hierarchies of cores, threads, then you've got multiple levels of cache, then you've got the RAM, and you've got interconnects. You've got the connections between processors, with QPI or Quick Path Interconnect on Intel, and Hypertransport on AMD. And it's an unfortunate reality, but it's not as simple as just writing some OpenMP loops. You really do have to have at least a certain level of basic level of knowledge about what the underlying hardware is like if you're going to write code that gets a reasonable proportion of our peak performance. And 2 very important things that we really need to understand are which cores our threads are running on. We call this CPU affinity, and exactly where the data that we're operating on is stored in memory. And we call this is related to the topic of NUMA and NUMA effects. And the best way to illustrate this is with a picture. So if you log on to many systems at CSCS, sometimes you have got to load up a module file, have this application called LSTopo. And LSTopo, if you're in the terminal and type it in, and you don't have X open, it will just give you some simple text output that will try to draw a diagram of exactly what the different processors and the different sockets look like, how much cache and how many cores they have. But if you run it with X on, you will get a little graphical window that looks like this. So this is what it shows us when we ran on a Sandy Bridge system. So I think this was generated on a Grainer, which is one of our systems here, which has exactly the same processors as we have in Pilatus. And we look at this and we see, first of all, that we have 2 sockets. We have a socket P0, or package 0, and another socket down here, socket P1. And you can see that attached to each socket, we've got something called a NUMA node, 16 gigabytes. And what this is saying is we have 16 gigabytes of RAM in something that we call the NUMA domain that's associated with this socket. And likewise, for the other socket, we have 16 gigabytes of RAM here. Now that means that on the node, we have a total of 32 gigabytes of RAM. And any of the cores, these are the cores enumerated along here, any core on any socket can access the memory in either one of these NUMA domains. But as we'll see later on, there's a big, it might look like a flat memory model, but there's a big penalty you can pay if a core, say this core over here, tries to access memory on this socket. And we can see that we have 8 cores on this socket, and each core has 32 kilobytes of L2 or L1 data cache, and also has its own private 256 kilobytes of L2, and then they have 20 megabytes of L3 that is shared between all of the cores. So yes, this is reasonably simple, as we're about to see. It might look quite complicated. And then, not illustrated here, is communicating between these sockets, we have something that Intel calls a QPI, a Quick Path Interconnect. So whenever, for example, this core here tries to access memory up here, that transaction, the memory will be transferred over the Quick Path Interconnect. If we do the same on Monte Rosa, which is our flagship Interlagos machine, we see a somewhat more complicated topology. So and we see, again, we have 2 sockets, a socket P0, so package 0, and another socket over here. So all of this is a socket, and all of this is a socket. Now this is on Monte Rosa, which has 2 Interlagos sockets. If you were to do the same thing on Toady, you would just have this side of the diagram, because it has 1 socket and 1 GPU. So we can see that we have but the main difference with the standard bridge is that each socket has got 2 NUMA domains on it. So we have a total of 16 cores, 8 cores associated with this NUMA domain here, which has 8 gigabytes of RAM on this NUMA domain, and 8 gigabytes of RAM on this one, and likewise here. And then we have 8 cores on each one. So you might have a case where even though a core is trying to access memory that's on the same socket, if this core here tries to access memory that's been allocated over on this NUMA domain, even though it's on the same socket, it's still not accessing local memory. It's going to be accessing memory on another socket, on another NUMA domain. So here we've got 2 sockets like before, but we've now got 4 NUMA domains. And we have what AMD call hypertransport. It's their equivalent to the Quick Path Interconnect. And hypertransport provides these fat links. So in theory, at least, where you should get the same bandwidth communicating between 2 NUMA domains on a socket as we would between the corresponding NUMA domains on the neighboring socket. And then we also have these skinny links, so we can also communicate directly between these NUMA domains like this. However, the communication speed is not as fast as if we communicate directly between these. And as you can imagine, it can quickly become a bit of a nightmare when you run your code on this and then you draw this diagram and you try to figure out from this diagram exactly what might be the issues with your code. And I'd say this is I think one argument why we like working with Standard Bridge so much more, is that this complexity just really makes life very difficult. Because you see, additionally, we have 2 cores here, and they actually share their L1 and L2 caches. So there's a lot more complexity in this design. And the final point is, you can't really expect to get very good performance on these sorts of architectures without having an understanding of all of this, of what's going on when you start trying to run multiple threads in your application. So this brings us to the topic of NUMA. So as we saw, if you have an OpenMP application running on your node, either one of those compute nodes, the threads running on any of the sockets or on any core will see one unified memory space. And they can freely access memory in any of that's allocated in any one of the NUMA domains. However, the time taken to access memory that is stored in different locations is not the same. And we saw on the first day when Neil got everyone to have a look at is it a hardware lock, Neil? Is that the application? And you saw you had that little map that showed the distances between the NUMA domains. And that's what this little map was talking about. It was trying to give a rough guide to the relative cost of fetching memory from different locations. And this sort of architecture is known as a NUMA architecture, which stands for non-uniform memory access. So yeah, the memory access times are not uniform depending upon where the memory has been allocated. And NUMA effects arise when we have when threads excessively access memory on different NUMA domain. It's okay if a thread if there's a little bit of information shared between NUMA domains. It only becomes a problem when this starts to occur a lot. And NUMA effects really have to be avoided, particularly on interlagos. So the whole point of this talk really is about understanding NUMA effects and some techniques that we can use to try and avoid them. And the idea of what we call affinity is essential to understanding and reducing NUMA effects. And there's really two types of affinity that we're concerned with. The first is CPU affinity, which is the pinning of your threads or processors to a particular core. So because often what will happen is if the operating system interrupts a thread for hardware access, for a hardware interrupt, once the interrupt is finished, the operating system will then start the thread up again, but it might start the thread up on a different core. And in a worst case scenario, it might start the thread up in a different core, on a different socket, for example, or in a different NUMA domain. So all the data it had in cache will no longer be local, and also data that might have been locally accessing will now be remote. So we need to have some way of controlling CPU affinity so that our threads don't migrate around like that, and we can say with confidence exactly where threads are running. And as we'll see, there are plenty of tools that are provided in these different HPC machines to give us this sort of control. And the final point is that the operating systems that run on our HP systems are stripped down and designed to minimize to the greatest extent the effect of hardware interrupts. Memory affinity is how we allocate memory so that it's as close as possible to the core, it's so that it's as close as possible to the core or the thread that's going to be accessing it the most. And both CPU and memory affinity are essential if we really want to maximize the memory bandwidth on NUMA nodes. So because if the memory affinity is not enabled, the memory bandwidth will be reduced because we have constantly fetching memory from another NUMA domain. So if we had to transfer information over the QPI or the hyper transport link. And if CPU affinity is not ensured, then you might lose memory locality. Even if you originally had memory locality, if your threads start migrating to another NUMA domain, you will no longer have memory locality. So first we're going to look at CPU affinity and how to set it using OpenMP. Now the new OpenMP 4 standard that was released recently actually standardizes some both environment variables and some runtime controls that you can use to get explicit control over CPU affinity, and they're very nice. However, the OpenMP 4 standard is still a long way from being finalized and implemented, so we're stuck with these ad hoc approaches taken by different OpenMP vendors. So if you use the GNU OpenMP, you will use a different technique to set CPU affinity than if you use the Intel or the PGI or the Cray. And some implementations are better than others. So for example, the techniques that Intel provides are actually very useful, and you can get very fine-grained control over your affinity. And you can also handle affinity using something like APRun, like the scheduler or the program that you use to launch your jobs. So APRun or SRun also have commands that allow us to set the affinity when we run. And Intel compilers use an environment variable called KMP affinity, and we can also get further control using this program called NUMACTL, which you will have seen if you looked at the script files for the programs we were running in the tutorial yesterday. Because in that tutorial, I wanted to have the most reproducible results I could get. And to do that, I needed to use something to ensure that I was always running my jobs on a single socket so that it wasn't set up differently between runs. So first, we'll have a look at the way Intel implements its Affinity controls. Now, as I said, you implement Affinity by specifying an environment variable. So you go export KMP Affinity equals, and then you give it a setting. There's two main options for this. So scatter Affinity. So let's say we have this theoretical dual socket system. So we've only got 2 cores per socket, and each have 2 hardware threads. So we've got hyperthreading on this socket. And an important thing to notice is that the way the hardware threads are numbered is like this. The first hardware thread on the first core is 0, and then we go to the next core, 1, 2, 3. So we've got a total of our 4 cores here. So the numbers are 0, 1, 2, 3 will number the first 4 cores on both. Will basically give you access to all of the cores on the 2 sockets. And then we go back to the start with like a round-robin numbering scheme. So hardware thread number 4, 5, 6, and 7. Now what happens if we set KMP Affinity and we ask for to scatter, and we ask for 4 threads? Oh, I should also mention there's an optional argument you can pass in here. You don't have to pass in verbose. Yeah, okay, I didn't debug this. That's true. So, okay. So there's an optional flag that you can pass in. And this will actually, whenever you run your OpenMP application, it will print out, it's about 2 pages worth of information telling you. It is very verbose, and it takes about 2 hours to really understand what it's telling you. But if you really want to see exactly what the topology of the machine is and exactly where the threads are being pinned, this information is very useful. So let's ask, so if we say OMP num threads equals to 4 and KMP Affinity equals to scatter, our 4 threads will be spread out this way. The first thread will be put on the first core, the second thread will be on the second core, and so on. So basically it will go through and assign 1 thread per core, which is what we want. Typically will be what we want, because this way, this thread here gets all of the resources on this core, this thread gets all of the resources on the second core, and so on and so forth. Then if we ask for 8 threads, it keeps the pinning we had before, and it just goes back to the start in a round-robin fashion, and then threads 4, 5, 6, and 7 get placed on the remaining hardware threads in the machine. The second commonly used setting is KMP, and again, this is obviously a cut and paste error. There should be an I there. Is KMP Affinity equals compact. And so the scatter approach basically tried to spread, you can think of it as trying to spread the threads out as far as possible from one another so that they're not all clustered together. Compact does the exact opposite. If we ask for 4 threads, it will place them as close together. So it will place them all on the first socket, which might be ideal for your situation. For example, if you've got 2 MPI tasks and you want 1 per socket with 4 threads each, this will most likely be the optimal setup. And then you ask for 8 threads. It then assigns the remaining 4 threads on the final core, on the final socket. Sorry. Is that clear enough? Now we have so that gives us a certain amount of control over how our application is launched. But if we're launching an OpenMP application on Pilatus, there's this program called NUMACTL, which is short for NUMA control, I think. It's not that well documented. Is a simple utility that we can use for controlling the placement of threads and memory on NUMA architectures. And you call it, if you want to, if executable is the name of the program you want to run, you call NUMACTL, you pass it some flags that describe the thread affinity and memory affinity that you want to use, followed by the name of your executable, and then if you have some command line arguments, you place them afterwards. And you can use this flag vCPU bind. This should be a hyphen. PowerPoint has gone and joined those together for me. And so you can use this to specify different configurations. So this first configuration here, if we're on a Sandy Bridge machine, cores 0 to 7, or I should say hardware threads 0 to 7, are the first 8 sockets on the 8 sockets on the first 8 cores on the first socket. So what we're saying here is we want our application to run basically on all of the cores on socket 1. This here, but we also have on each core on our Sandy Bridge has 2 hardware threads, and those hardware threads, the second set of hardware threads is numbered 16 to 23. If we go back to our example here, you see how we numbered the hardware threads 0, 1, 2, 3, and then for the second hardware thread on each core, we start again in a round-robin fashion, 4, 5, 6, 7. So if you have 8 cores per socket, this here, 16 to 23, will be the second set of hardware threads on the first socket. And then this here will just use the physical cores or the first hardware thread on both sockets. So 0 to 15, that's the first 16 cores. And furthermore, we can control where memory is bound. So when we allocate memory, say using a malloc statement, it will then pin we can tell it to, by default, pin the memory explicitly in a particular NUMA domain. So we could say membind equals 1, and it will pin the memory in NUMA domain 1. If we say membind equals 0, you can pin the memory on NUMA domain 0. And later on in the examples, what we're going to do is we're going to pin all the cores to run on one socket, and then pin the memory to be all in another NUMA domain, and then see what impact that has on performance. So now we're going to do a little exercise. You can log, and we're going to do it on Pilatus, and the idea is just to familiarize yourself with how you can use the KMP Affinity and NUMACTL to control the CPU affinity or pinning of threads when you use the Intel compiler. So I have added, overnight, I added this directory here. So you can copy that into your Scratch on Pilatus, and it has a make-file. So once you've loaded the Intel module, you can make affinity.intel, and then you can just experiment with just for starters, just run affinity.intel without any flags and see what output it gives you. But it's a little application that for each thread in your program, it will print out which cores the thread has affinity with. And you don't actually need to use srun for this because it's just a tiny little application, and the login nodes use Sandy Bridge. So you can just run it as is, and then there's a few little examples you can just go through using one OpenMP thread or 16 threads, and then to see if we can use NUMACTL and the KMP Affinity to pin 16 threads, one per physical core, and so on. Okay, so socket 0 and socket 1. And then we have, this is always a challenge. It was easier when there were only 2 or 4 cores per socket. It's getting harder as they add more and more cores to do these pictures. So when we number the cores, or the number of threads, 0, 1, 2, 3, 4, 5, 6, 7 is the number of the first hardware thread on each core in our socket 0, and then we start on the next socket. So we go 8, 9, 10, 11. And then we start again. So 16, 17, 18, 19, 20, 21, 22, 23. So the hardware threads 0 and 16 are on the first core. And then 1 and 17 are on the second core on the first socket. So the first socket has threads 0 to 7 and 16 to 23. And then likewise for the second socket, we start at 24, 25, ... to 31. Now, hopefully you can read that at the back, get an idea. But yeah, socket 0 has 0 to 7, 16 to 23. Can this be reconfigured by the operating system? I mean, I think it can be, and I think you can actually do it, but it's quite consistent generally. I mean, all of our Sandy Bridge systems use this same numbering scheme. And you can figure this numbering scheme out if you set like KMP affinity equals scatter or compact, and then a comma verbose. From that verbose output you get, you can determine exactly what numbering scheme the operating system has given. But it takes a little bit of time to figure that out. Oops, okay. So I'm just going to run through a couple of little examples. It's all been set up for me already. Okay, I'll start again. So I load the Intel module file. And I make affinity.intel. And then if I just run it, I get the following very verbose output. So what is this telling us? Well, it's telling us that if I start at the start, it tells me that, and the threads aren't printed out in order. But so it's telling me it starts with thread 19. Thread 19 has affinity with 0 up to 31, which means that the operating system is free to place thread 19 wherever it pleases. And the same goes for thread 31. In fact, the same goes for all of the threads. So this is we don't have any real control over what we're doing. And we can say, well, if someone says, which NUMA domain is thread 5 going to be in? And you will say, I don't know. And by the way, the default is OMP num threads equals 32. That's why it's given us output for 32 threads. So let's go to num threads equals 8. And do it again. Okay, we get output just for 8 threads. Now I'm going to start by looking at the different affinity settings. So KMP affinity equals scatter. Actually, I'm going to do compact. So I see that thread 0 has got affinity with 0 and 16, which is quite good because 0 and 16 are both on the first core. They're both on core 0. So I'm quite happy with that. That means thread 0 is always going to be on core 0. And then I go down and let's see where thread 1 has been put. Thread 1 has also been put on the same core. It's been put on 016. Now this is not necessarily a good thing because this means that both thread 0 and thread 1 are on the same core. They're both going to be sharing the same L1 cache and the same L2 cache. So let's go with this. Let's pretend that we've got 8 threads and we would like to place them on one socket with one thread per core. Well, let's see, what does our scatter do for us? Now again, we see, what have we got? Thread 0 is again on the first core, 0 and 16. And thread 1, where has thread 1 been put? Thread 1 has been put on 8 and 24. Now, what's that? So we've put thread 1, thread 0 has been put here. 8 and 24 is here. So it's actually placed the next thread on the first core of the second socket. And then if we look at our thread, thread 2, which is the third thread, it's been put on 117. So 117, that's the second core of the first socket. And then thread 3 has been put on 925, so that's the second core of the second socket. So you can see what it's doing. It's getting the threads and it's putting one here, the next one here, one here, the next one here, one here, the next one here. So we're getting the right sort of setting. We're getting one thread per core, but now the threads are getting distributed between the cores, which might be a good thing, but I'm interested in getting all of the cores, all 8 threads running just on the first socket, one thread per core. So I can then use NUMACTL, vCPU bind. So remember, with vCPU bind, you can specify a range or a set of values of cores that you want to run on. So you can do that by, I want it to run on these 7. So this is, I want you to specifically place on between 0 and 7. Now this is looking a lot better. Now we have thread 0 is on CPU 0. Thread 1 is on CPU 1. Thread 2 is on CPU 2, etc. We've achieved what we wanted to. But we noticed before that it was putting, we don't have the hyperthreads here. We don't have the second thread per core. To do that, we can also enter in those threads. And an easier way to type from 0 to 7 is just to use this, a 0 or -7. And then I also want to include threads 16 to 23. And here we go. Thread 0 has got its choice between the 2 hardware threads or hardware cores on core 1 or core 0, and thread 1 likewise is now on core 1, and so on. PowerPoint, where are you? That seems to have gone forward. So as a final little task, can you do 16 threads? So when I talk about a physical core here, I'm just talking about the first hardware thread on each core. So I would like to have 16 threads. Thread 0 on core 0 or CPU 0. Thread 1 on CPU 1, and so forth, all the way through, covering both sockets. It's quite simple. I would ask for threads 0 to 15. That's the first 16. And I'm going to set OMP num threads equals 16. And here we go. We have the first thread is on CPU 0. The second thread is on, what's it done here? It's actually put the second thread on 8. which is okay. Then they're not on contiguous. So what that's going to do is assign the 16 threads, but it's going to put them like this in this pattern. So it's going to interleave them. And I haven't given the example here, but there's also another option besides scatter and compact. You can say that the option explicit, and then in equals, then in curly braces, you can type in exactly an exact list of thread cores that you want to have affinity with. Will that work? Okay. So has everybody finished up there? So on the Cray systems, we go about setting thread affinity a little bit differently, and the Cray system actually has it's a much nicer way of setting affinity. So if you go on to the Cray systems here use Interlagos. I don't know what's going to happen on our new Cray system, which uses Sandy Bridge, but if you compile using the Intel compiler on our Interlagos machines, and then set KMP affinity and try to run your program, you'll get a warning message saying from the Intel OpenMP saying, it's an Interlagos. I can see that you're trying to set affinity, but I'm just going to ignore what you're doing because I don't want to do that for Interlagos. But that's okay because AP Run provides us with some tools for setting affinity. And I'll just skip down to here. AP Run has got a very good manual page. So if you type in man AP Run, it gives you all the flags with very extensive descriptions. And it also has lots of examples. So it's got pages and pages of examples for how to set up different scenarios. And many of these options are concerned about when you have multiple MPI processors on a node. So let's say you've got 4 MPI processors running on a node and you want to set the thread affinity in different ways. Most of the options are for that sort of a thing. But if we just want to have a little look at running a simple OpenMP application, I'm going to look at the -CC flag. And -CC is very similar to vCPU bind in that you give it a list of cores on which you want to have affinity. Now you don't have to go setting any environment variable because AP Run will automatically go and then assign affinity. And if you don't want it to actually pin individual threads to individual cores. So put thread 0 on core 0 and thread 1 on core 1 and so on and so forth. You can use this flag -CC NUMA node. What NUMA node will say is, I want all the threads to be assigned to cores on the same NUMA node, but I don't want you to explicitly pin each thread to an individual core. They can float around on those cores. So that's what we're doing. This will do so 0 to 3 will do round robin. So this can be a little bit of a problem if you, say, have 8 OpenMP threads, and you tell it that you want to pin to 0 to 3, so only onto 4 sockets. What it'll do is it'll pin the first thread on core 0, the second on core 1, the third on core 2, the fourth on core 4, then it'll go back to the start and pin the fifth on core 0, core 1, core 2, core 3, and then you'll notice straight away that instantly your performance will get very bad because you're trying to run 2 threads on a single core, which for Interlagos is a bad idea. And again, this is just an example that instead of having a hyphen to give a range, we can just type out a list. And we can have 2 hyphens in a list, and then the NUMA node. So the NUMA node's interesting because then the pinning they can float around on the 8 cores in a NUMA node. Because remember that the Interlagos from the diagram before had 2 NUMA nodes in each socket, and each NUMA node had 8 cores on it. Okay. So, the thing is, you might have your AP run command all set up to get a good pinning on Interlagos machine, on Toady, which has 32 cores, but then you might want to go and run your application on the new Sandy Bridge machine. And you'll probably have to change your AP run line because the standard bridge with the hyperthreading, fundamentally it's a different numbering scheme and a different way of organizing your processor. So you will have to go and change the affinity, and that's true for each different machine you run on. If you run on a machine with 8 cores or 4 cores or 16 cores. So this little application that we used in the last example, using a tool like that which will print out to the screen exactly where the thread affinity is, that's a very good tool to use to just try and figure out exactly what the thread affinity you want is, and then use that to run your actual application. So you can take this code home and use it again. It's a very useful tool. So the second little miniature exercise is very similar to the last one we did, but this time we're going to log on to Toady, or you can also log on to Rosa if you want to play with a more complicated domain. So Toady just has one socket. Each socket has 2 NUMA domains with 8 cores each, and just play around with using AP run. So you have to get a session, so salic -n1, and then play with these options for a few minutes. So the aim here isn't really for you to memorize all of this, it's just to show you the sorts of tools that are available so that later on when you want to do this, you know where to go looking. Okay, would people like me to quickly run through that on a terminal window, or did you all basically get the idea? I see most people nodding their heads. It's not a very difficult or sophisticated example. Just wanted to get you used to these sorts of settings. Okay, so now that we can assign pin threads where we want them on our sockets, we can start to think about different techniques for handling NUMA effects. So when we realize that we've got a NUMA-related problem or bottleneck in our code, how do we go about addressing it? And there are 2 basic methods. Easily the best method is to use a hybrid MPI OpenMP code, where you have one MPI task per node and then threads inside that per OpenMP task. So for example, on our Sandy Bridge architecture that we had back at the start, it's a bit too far back, you would have 2 MPI tasks, 1 per socket. And each MPI task might have 8 or 16 threads with all those threads running on that socket, which means that a thread in an MPI task can never access memory that's on a different NUMA node because that MPI task is locked onto that NUMA node. This is by far and away the preferable technique. On Sandy Bridge, NUMA effects are not as strong as they are on Interlagos. On Interlagos, if you start trying to communicate information between NUMA domains, it gets very slow very quickly. But Sandy Bridge is actually quite tolerant of that, so you can. But typically, you will want to just use this approach of one MPI task per NUMA domain. But if you really do want to run an OpenMP application that works across multiple NUMA domains, you can use what we call the first touch memory allocation. Now, first touch memory allocation is the default way that most Linux kernels will allocate memory. And the important idea here is that when you allocate memory using something like a malloc call, for example, that memory is not actually pinned anywhere. It's pinned to a particular NUMA domain the first time it is touched, or the first time it is set. So, for example, you might allocate the memory 1,000 bytes, and then you might loop through that memory and set all the values to 0. When you set them to 0, that's when the memory gets allocated to our NUMA domain. And it gets allocated to the NUMA domain of the thread that first touches it. Now, this leads to an obvious problem, because what most people do when they allocate their memory is they allocate their memory for storing their matrices or their buffers or whatnot, and then they just have a simple for loop that goes through and loops and sets it all to 0 or 1 or whatever the values are, and they don't put an OpenMP statement on that loop. So basically, the first thread 1, which is the only thread running outside of the OpenMP region, will go through and initialize all the memory. So all the memory will get put on the NUMA node of thread 0. And then when you go into your parallel regions and all of your other threads try to access that memory, they're going to access memory on that whatever NUMA node your first thread was on. So what we want to do is we want to actually parallelize the initialization. So if you've got to set up your initialization, you've got to look at inside when I run my threading regions, do I access the memory in blocks or in strips or whatnot, and figure out which threads touch which memory, and then set up your initialization phase so that the memory is first touched by the threads that are later going to use it. And there's a big capture here. Particularly in the C library, there are a bunch of ways you can allocate memory that will actually initialize it for you. So in the old standard C library, there's a calloc routine. I don't know if it's actually part of the standard C library. You shouldn't ever really use this routine, but this routine will actually allocate the memory, then initialize it to 0 for you, which is a very bad idea. You don't want to use that. You don't have that problem if you use malloc. Malloc just allocates the memory but doesn't touch it. And if you allocate using the standard allocator in C++, and the standard allocator is used whenever you declare an STL container type, like a vector or a list or a map. It also, if you go and look inside the definition of that allocator, it actually goes through and initializes the values to 0. So if you want to use an allocator in C++, you can go through, basically cut and paste the standard allocator and then modify it so that it doesn't initialize the memory when it allocates it. And then you can later on go, or you can write your own custom allocator that will have an OpenMP loop in it and initialize the memory. Now, an important thing to remember is that it doesn't just say, oh, this thread touched this double, and this thread touched the double next to it, so we're going to put them on different NUMA domains. What it actually does is it breaks it up into pages, 4 kilobyte pages, and the first thread to touch a whole page, a whole 4 kilobyte page, that 4 kilobyte page will get put into that thread's NUMA domain. So you can be careful. You have to be careful because these 4 kilobyte domains might actually be accessed by different threads. So it can actually be very difficult to set things up so that you completely remove references for where one thread is accessing memory in another NUMA domain. You just have to be aware of these things. So you have to try and set your block size, your granularity to be as large as possible to minimize this effect. So here's a really simple example. I allocate a couple of arrays that are about 8 megabytes in size, A and B. And then a normal way to go about it might just be I'm going to set A to be the square root of B. And if I've just gone and initialized this memory previously without using an OpenMP statement, all this memory is going to be stored on wherever thread 1 is, and you're going to have a problem. So in this case, it's very simple just to do a pragma OMP parallel 4. When you initialize the memory, so initially I set A to be 0. Technically, I don't really have to initialize A because A will get initialized here, but it's good to initialize it, and I set B to be equal to 2. So, but of course, you can imagine if you have a more complicated algorithms that access data in block patterns or whatnot, it's going to be your initialization routine might end up looking a bit more complicated. So let's have a little look at a very educational example. Who here has heard of the stream benchmark? Okay, now the stream not anybody. Now the stream benchmark is it's a very simple diagnostic tool that usually whenever we get a new system, everyone here will compile the stream benchmarker and run it and see what numbers they get. The stream benchmark is a basic test for testing memory bandwidth, and it runs 4 different tests. The first test just copies a block of memory into another block of memory. So it just copies one array into another array and measures the bandwidth. And then we have 3 other tests that also do a little bit of arithmetic. So they might load one array, multiply it by a scalar number, then write the result back into another array. And then another one that will load 2 arrays, add them together, and then store them back into another buffer. So we're going to look at different ways of setting up your memory affinity with the stream benchmark. So the first way we're going to do is where we set up our memory affinity properly. So we allocate these arrays that we're going to be copying to and from, And then we have a for loop that has been parallelized using a Pragma OMP parallel for, so that the parts of each array that each thread is going to be touching will be in the appropriate, will be in the right NUMA domain. So the parts of the 3 arrays we use 3 arrays, A, B, and C, that this core will use will be allocated here. This core will use the parts also here. So this is our ideal or best case scenario. The second is going to be what we might think of as a worst case scenario. So we go through and we set up the initialization phase that all the wrong threads touch all the wrong data when they initialize it. So this thread is always going to be accessing memory that's stored in another NUMA domain. So all these threads will access this NUMA domain and all these threads will access this NUMA domain. And the third is what typically will happen if you just have a simple for loop to initialize your data. The first thread 0 will go and initialize the data, and all of the data will end up being on NUMA node, this first NUMA node. Now, does anybody want to have a guess at which will be the worst performing of these two? I got it wrong, by the way, when I had a guess before looking at the results. Yes, JG, up the back. Number 3. JG guesses this one's going to be the worst performing, which might be a little bit counterintuitive, but it's a good educated guess. So yeah, so this of course relies on the fact that we have enough memory on one of the sockets or one NUMA domain to hold all of the data, which we do. Okay. And here are the results. Now this isn't for any system we currently have at CSCS. So I got these results from Neil, from a benchmark Neil did, and he did it on Rosa, but he did it on Rosa. Rosa was upgraded. I don't know how long ago. It was from before I got here, but over a year ago, Rosa had its processors upgraded. But it had a very similar architecture: 2 sockets, and each socket had 2 NUMA domains in it. And these are the results. So here we have the memory bandwidth measured for the 4 different tests. So the basic copy, and then the 3 tests that do a little bit of arithmetic. And this is when the memory affinity has been set up properly. So when the memory affinity is like this. And we see we get 47 or 48 gigabytes a second for copy, and about 34 to 37 gigabytes a second for the other operations. Then when we have the inverse affinity, that's when basically each processor has to go to another NUMA domain to get its information. We see the bandwidth is about half, nearly exactly half. And then when we have the first touch, thread 0 did the first touch, the performance really drops through the floor. It gets very poor. So this is a factor of 5, 6 times worse. And what's happening here is that when we allocate memory like this, we're still utilizing the resources quite well, in that the maximum amount of bandwidth available from this memory is available. It's just that we're trying to squeeze the memory through this hypertransport connection between the two NUMA domains. So that's the bottleneck. But in this case, we have 2 sockets trying to, or two different sockets trying to access memory in one location, and it just puts too much strain on the memory transfer architecture. So initially, I thought this would actually be worse, but this one is actually a worse setup, because we've got potential bandwidth from this memory, and we're not touching it. We're not using it at all. And you can see that you get very, very poor performance. You might say, well, my theoretical peak bandwidth is X, and I'm seeing only at least 5 times slower. And the reason is by putting if you put a simple OpenMP loop around your initialization, you would have had results that were of the order 5 to 6 times better. So this is, I think, a very good illustration of why this is very important. Now, for the rest of this, we're going to look at some extended examples. So we're going to revisit the Laplace and dispersion examples that we looked at yesterday. So people might have noticed, or quite a few people commented to me that they might have seen scaling up to 8 threads, but then the 16-thread results were the same, or no faster. And they were wondering why that was. And I was using NUMACTL to pin the threads correctly, so we had 1 thread per core, but there was absolutely no benefit going from 8 threads to 16 threads. And the reason was due to NUMA effects, because the initialization loops were doing first touch policy without any threading. So all the memory was being allocated on one NUMA domain. So just go through these steps here to first look at the Laplace OpenMP example and see, just first of all, without changing anything, just try and run it with 1 thread or 8 threads and try pinning the process to run on 1 socket and then pinning the memory on another socket or on the same socket and see what sort of performance hit. Is it 20% slower? Is it 50% slower? What sort of performance difference does it make? And you should see a pretty significant difference because this is a memory bandwidth bound code. And then once you've figured out that, once you can see that there is definitely a difference between getting memory in the right spot or the wrong spot, have a look at find the initialization loop in the Laplace OpenMP.c and change it to use some OpenMP statements and then see if that improves the 16-threaded results. And then, task 2, we can repeat that with the dispersion example. The dispersion example is a bit more complicated for version 3 of the stencil. You've got to now change 2 spots in the code to make it work. And then task 3, we can do these tasks again on Rosa. And you should see on Rosa, that on Standard Bridge, it's not too sensitive to these NUMA effects, but then when you copy the code over to Rosa, you will hopefully see that it is really sensitive to these NUMA effects. And it's very important there to make sure that you do first touch properly. One thing to remember to do when you're running on Pilatus is always to use srun, and say srun NUMACTL, whatever. Otherwise, you're running on the, I've seen a few people doing it now, because otherwise you're actually running on the login node, and everyone else is doing their compilation and vi editing, Emacs, whatever editing on that node, so you're probably not going to get some state. So let me see. So let's see. 16 threads. Okay. Okay, so what we're interested in is for the larger problem, so the 2050 by 2050 grid. And we can see that before we got reasonable speed up, however, it was bandwidth limited up to 8 OpenMP threads. But then you would expect when you went to 16 OpenMP threads, you would expect to see some more speed up because you would then be using the memory on the second socket, so you would have double the memory bandwidth and you would expect to see these times go down, but we've only got about a 6% reduction in bandwidth. So there's something going on there where I would, oops, what am I doing? So if I go into the source code, you might have found this set init conditions on line 28 is where the initial conditions are set, and we can see that we have this loop here that loops over j and loops over I and initializes each of the field that's passed in to 0. And this is called twice, once for the field, the input, one for the infield and one for the outfield. So the trick is to add a simple pragma OMP parallel 4 around that loop, because if you go down to the other loops below, where we added the OMP parallel 4s, they also had a J loop on the outside, I loop on the inside, and then accessed the data in that order. This is maybe a simpler one. Yep, so that's all we have to do. And then I make OpenMP. And then hopefully, there's always a danger when you do live demonstrations like this that it doesn't work. So I'm going to take that risk. So things went slower, didn't they? Let's have a look. So did anybody do this and actually get it to go faster? Okay, that's encouraging. Okay. I actually saw some people who did it and got it to go faster. Ah, that is actually a mistake. It shouldn't make much difference, but, well, let's see. Oh, that actually made a massive difference. It made it worse. Okay. Equals compact. Okay, that sped things up a little bit. So I definitely have that set. Now, when I tested this yesterday, it worked perfectly. Now, some people did get this to work though, didn't they? Let's have a look. Let's have a look at what affinity we've got. So thread 0 is on 0, thread 1 is on 1, so that affinity looks good. Okay, so I don't know what I was thinking there, but so this is the, so I should have, first of all, I wasn't using srun, which I should have been using. But yeah, so this is when I had the OpenMP directives in, the times were 0.27, and then when I remove the OpenMP directives and recompile, the times go up to about 0.6. So we've got a factor of 2 speed up just by adding that initialization. Now, so that was with affinity equals compact. if we set it to scatter, thank you, Neil. Module, what am I doing? What I'm expecting is to see that it's not as fast as it was with compact. And it's a little bit slower, but not too much worse, actually. So I think someone else, you saw earlier that it was different if you used compact and scatter, didn't you? But for me, it's not making... Oh, okay. Because yeah, with compact, if you set it to compact, it sets threads 0, 1, 2, 3, 4, 5, 6, 7. So the first 8 threads go on socket 0, and the second 8 threads go on socket 1. If you set it to scatter, it goes thread 0, thread 1, thread 2, thread 3, thread 4. So you get this interleaving. So you're more likely to have some, maybe the data access patterns are going to be interleaved, and you might actually have some conflicts. Okay. So how much more time have we got, Neil? 0. Okay, then I will unplug. Okay, well, I thought just one final thing I would show to people. Won't necessarily run it to get results, but I'll just show how to update the dispersion example if people are looking at that. If you want to figure it out for yourself, then just look away. But, so we have to set initial conditions. We have to update that as it was before. But there is another spot in the code, so that will speed up the performance for version 1 and version 2 because they use the sin, sout, and this global buffer. Those are the only fields they use, and all 3 of those are initialized using this routine. But version 3, also each thread has its own private, the little block buffer that it uses for intermediate computation, and those are initialized down here in the main program. You can see we allocate a pointer or a pointer to a pointer for doubles. Basically what this is doing is we're going, now we array for each thread, num threads, we allocate an array. And then here, this is a loop that loops over each of these little buffers, allocates the memory, and initializes it to 0. So at the moment we see we just loop over the threads using a for loop, and then we get the pointer to the buffer for thread TID, and then we allocate the memory and initialize it. Now the way I would go about doing this is to comment out the for loop there, make a, pragma OMP parallel 4. Oh, no, we don't make that a 4. So what this will do is this will start up a parallel section with 8 threads or 4 threads or however many threads. And then we want to get our thread ID. So int thread ID is equal to OMP get thread num. Okay, so what this does, this gets the unique integer that defines this thread, so maybe thread 0 or thread 7 or thread 8. And then then the thread will go and get a point, will allocate the memory for its buffer, and the thread will go and initialize the memory for its buffer. And that way each thread allocates and initializes the memory for its own buffer, and that means, so all of these fields should now have been initialized in such a way as to make it a first touch policy work. And when I tested this the other day, I got speed up of about 60%, I think, over. So this version of the code doesn't actually have any. Oh, it's got the OMP loops in it. So did anybody actually do the dispersion example and get any results? Okay. Yeah, it's a little bit tricky figuring out this final step here, but it was only required for version 3. Versions 1 and version 2, you should only have to make the same change that you made to the Laplace.c file. Okay, and now I'm going to hand over to Neil. In any of the, that's allocated in any one of the NUMA domains. However, the time taken to access memory that is stored in different locations is not the same. And we saw on the first day when Neil got everyone to have a look at is it a hardware lock, Neil? Is that the application? And you saw you had that little map that showed the distances between the NUMA domains. And that's what this little map was talking about. It was trying to give a rough guide to the relative cost of fetching memory from different locations. And this sort of architecture is known as a NUMA architecture, which stands for non-uniform memory access. So yeah, the memory access times are not uniform depending upon where the memory has been allocated. And NUMA effects arise when we have when threads excessively access memory on different NUMA domain. It's okay if a thread if there's a little bit of information shared between NUMA domains. It only becomes a problem when this starts to occur a lot. And NUMA effects really have to be avoided, particularly on interlagos. So the whole point of this talk really is about understanding NUMA effects and some techniques that we can use to try and avoid them. And the idea of what we call affinity is essential to understanding and reducing NUMA effects. And there's really two types of affinity that we're concerned with. The first is CPU affinity, which is the pinning of your threads or processors to a particular core. So because often what will happen is if the operating system interrupts a thread for hardware access, for a hardware interrupt, once the interrupt is finished, the operating system will then start the thread up again, but it might start the thread up on a different core. And in a worst-case scenario, it might start the thread up in a different core on a different socket, for example, or in a different NUMA domain. So these are the cores enumerated along here. Any core on any socket can access the memory in either one of these NUMA domains. But as we'll see later on, there's a big. It might look like a flat memory model, but there's a big penalty you can pay if a core, say this core over here, tries to access memory on this socket. And we can see that we have 8 cores on this socket, and each core has 32 kilobytes of L2 or L1 data cache, and also has its own private 256 kilobytes of L2, and then they have 20 megabytes of L3 that is shared between all of the cores. So yes, this is reasonably simple, as we're about to see. It might look quite complicated. And then, not illustrated here, is communicating between these sockets, we have something that Intel calls a QPI, a quick path interconnect. So whenever, for example, this core here tries to access memory up here, that transaction, the memory will be transferred over the quick path interconnect. If we do the same on Monte Rosa, which is our flagship interlagos machine, we see a somewhat more complicated topology. So and we see, again, we have 2 sockets, a socket P0, so package 0, and another socket over here. So all of this is a socket, and all of this is a socket. Now this is on Monte Rosa, which has 2 interlagos sockets. If you were to do the same thing on Toady, you would just have this side of the diagram, because it has 1 socket and 1 GPU. So we can see that we have but the main difference with the standard bridge is that each socket has got 2 NUMA domains on it. So we have a total of 16 cores, 8 cores associated with this NUMA domain here, which has 8 gigabytes of RAM on this NUMA domain, and 8 gigabytes of RAM on this one, and likewise here. And then we have 8 cores on each one. So you might have a case where even though a core is trying to access memory that's on the same socket, if this core here tries to access memory that's been allocated over on this NUMA domain, even though it's on the same socket, it's still not accessing local memory. It's going to be accessing memory on another socket, on another NUMA domain. So here we've got 2 sockets like before, but we've now got this. We've now got 4 NUMA domains, and we have what AMD call hypertransport. It's their equivalent to the quick path interconnect, and hypertransport provides these fat links. So in theory, at least, where you should get the same bandwidth communicating between 2 NUMA domains on a socket as we would between the corresponding NUMA domains on the neighboring socket. And then we also have these skinny links, so we can also communicate directly between these NUMA domains like this. However, the communication speed is not as fast as if we communicate directly between these. And as you can imagine, it can quickly become a bit of a nightmare when you run your code on this and then you draw this diagram and you try to figure out from this diagram exactly what might be the issues with your code. And I'd say this is I think one argument why we like working with Sandy Bridge so much more is that this complexity just really makes life very difficult, because you see additionally we have 2 cores here and they actually share their L1 and L2 caches. So there's a lot more complexity in this design. And the final point is you can't really expect to get very good performance on these sorts of architectures without having an understanding of all of this, of what's going on when you start trying to run multiple threads in your application. So this brings us to the topic of NUMA. So as we saw, if you have an OpenMP application running on your node, either one of those compute nodes, the threads running on any of the sockets or on any core will see one unified memory space. And they can freely access memory. Okay, I think we've got everybody here. So this afternoon, I'm going to talk about some very important, a very important topic if we want to get good performance using these multi-core architectures like the Interlagos and Sandy Bridge that we've been looking at during this workshop. And you will have already seen, particularly during the exercises and during the talks, you'll have seen some strange behavior, particularly when you try to use, say, 16 threads on Sandy Bridge and you don't see the sort of speed up you might expect to see. And you've seen people talk about Affinity and whatnot. So now I'm going to go into some more detail on these topics. Oh. And I'm going to turn that on. So I'm going to start the talk today with just an overview of the Interlagos and Sandy Bridge topology and point out some key similarities and differences between the 2 architectures, and we'll start to get an idea about how some of these features might affect performance when we try to scale to using multiple sockets. We'll have a look at what we call our NUMA effects, and then we'll look at something called our CPU affinity and memory affinity, where we can get more fine-grained control of exactly where our threads, like which cores our threads are running on, and finer-grained control over where exactly in memory we store the data that we want to operate on. And then we'll look at we'll do some methods and exercises to illustrate this point. And then at the end, we're going to do some extended examples where we're going to revisit the Laplace and dispersion examples from yesterday and see if we can make some changes to the code to get some good performance increase when we go from 8 threads running on one socket to 16 threads running on 2 sockets. So far, I'm pretty sure you've got the impression from the work we've done so far that these multi-core and many-core processors have really quite complicated architectures. You've got these hierarchies of cores, threads, then you've got multiple levels of cache, then you've got the RAM, and you've got interconnects. You've got the connections between processors with QPI or quick path interconnect on Intel and hypertransport on AMD. And it's an unfortunate reality, but it's not as simple as just writing some OpenMP loops. You really do have to have at least a certain level of basic level of knowledge about what the underlying hardware is like if you're going to write code that gets a reasonable proportion of our peak performance. And 2 very important things that we really need to understand are which cores our threads are running on. We call this CPU affinity, and exactly where the data that we're operating on is stored in memory. And we call, this is related to the topic of NUMA and NUMA effects. And the best way to illustrate this is with a picture. So if you log on to many systems at CSCS, sometimes you have got to load up a module file, have this application called LS-Topo. And LS-Topo, if you're in the terminal and type it in, and you don't have X open, it will just give you some simple text output that will try to draw a diagram of exactly what the different processors and the different sockets look like, how much cache and how many cores they have. But if you run it with X on, you will get a little graphical window that looks like this. So this is what it shows us when we ran on a Sandy Bridge system. So I think this was generated on a Grainer, which is one of our systems here, which has exactly the same processors as we have in Pilatus. And we look at this and we see, first of all, that we have two sockets. We have a socket P0, or package 0, and another socket down here, socket P1. And you can see that attached to each socket, we've got something called a NUMA node, 16 gigabytes. And what this is saying is we have 16 gigabytes of RAM in something that we call a NUMA domain that's associated with this socket. And likewise, for the other socket, we have 16 gigabytes of RAM here. Now that means that on the node, we have a total of 32 gigabytes of RAM. And any of the cores